continue with the next set of instruction, that is multiplication of 32-bit instructions. So we have two operations here, one for signed multiplication, another for unsigned multiplication. So first, let us see the first instruction under multiplication of 32-bit instruction. In the previous session, we have seen just the instruction MUL, the mnemonic MUL. So whenever if you use this instruction, the result of the 32-bit multiplication, we assume it to be as 32-bit result itself. Therefore, we have only single destination register here. But that will not be true for all the cases. The result of 32-bit multiplication might give you a 64-bit answer. Therefore, in this instruction, that is signed long multiplication, we have two destination register for storing 64-bit result. Now we have two source registers here. The instruction syntax is SMUL, that is signed long multiplication, RDL0, RDHI, RN, RM. RN and RM are the source register, and we have two destination registers here. So this instruction multiplies two 32-bit register contents, and the resultant 64-bit answer will be stored in the two destination register RDL0 and RDHI. So out of 64-bit result, the least significant 32-bit result will be stored in RDL0, and the most significant 32-bit result will be stored in RDHI. So the next instruction is SMLAL, that is signed long multiplication with accumulate. Signed long multiplication with accumulate. So space SMLAL space RDL0, RDHI, RN, RM. So these two are the source registers, and we have these two registers as destination register for storing the result. Now you have, along with the multiplication, you have one more operation, that is accumulate operation. So along with multiplication, you have one more operation called accumulate. Now let us see what it is. It multiplies two 32-bit registers RN and RM, and you get a 64-bit result out of this multiplication. That 64-bit answer, what you get after multiplication, will be added with the content of RDL0 and RDHI, and after summation, whatever the result you get, that will be stored in RDL0 and RDHI. So it is the first operation. It performs two operations. One is multiplication of RN and RM, and the second operation is the addition of the result of the multiplication along with these two destination registers. So finally, after these two operations, the 64-bit data will be stored in the destination registers RDL0 and RDHI. So next instruction is unsigned long multiplication, RDL0, RDHI, RN, RM. Now here it will multiply two 32-bit data which is present in RN and RM. The result will be stored in 64-bit result will be stored in RDHI and RDL0. So this is about unsigned long multiplication. So here the data will be considered as unsigned data. Next you have unsigned long multiplication with accumulate. Unsigned long multiplication with accumulate. So here the two registers, source registers, which is having 32-bit data. Again, as you have accumulate, we have two operations. The first operation is multiplication operation. Second operation is addition of the result of multiplication and the content of RDHI and RDL0. Now let us see what is the first operation. The first operation is multiplication. That is, the content of Rn will be multiplied with content of Rm. Now you get the 64-bit result from this multiplication. That result will be added with the previous content of RDHI and RDL0. Now after summation of this operation, then the result will be stored in RDL0 and RDHI. So that is, it is performing two operations. One is multiplication, then addition. So hence we have long multiplication along with accumulate. So this operates for unsigned data. Now let us see the example of these instructions. simple example each. Now, first example is UMULL, that is unsigned long multiplication. There is no accumulate operation here, just multiplication. So we have the registers RDL0 as R0, RDHI as R4, RN as R5, and RM as R6. Now what's the source registers here? R5 and R6. It will multiply the content of R5 and R6. The result of the multiplication will be 64-bit data. That 64-bit data is stored in R0 and R4. So the least significant 32-bit of the result will be stored in R0. The most significant 32-bit of the result will be stored in R4. This is about the operation UMUL. The next example is SMLAL, that is signed long multiplication with accumulate. Signed long multiplication with accumulate. So here you have two operations. First one is multiplication, second is addition. Okay, so let's see the registers operand fields here. So RDL0 is R4, RDHI is R5, R3 is RN, and RM is R8. Okay, so what is the first operation? Source registers will be multiplied. So R3 content and R8 will be multiplied, and you will get a 64-bit result. That 64-bit result will be added with the content of R5 and R4. Now after this operation, whatever the 64-bit data you get, the least significant 32-bit will be stored in R4, and the most significant 32-bit result will be stored in R5. So this is about the operation signed long multiplication with accumulate. I hope you have understood, and these instructions are important. Next, we will move to the logical, the simplest operations, that is logical operations. Now we the basic operations and logical operations are and, or, not, XOR. So all these are negation. All these are the basic logical operation. And we know that all logical operations are performed in bitwise. So each register will be represented in a bitwise, and the operation will be performed. Now first set of instruction is AND operation. Let us see each instruction one by one. And RD, and space RD comma RN. So the content of RD will be bitwise ANDed with the content of RN. Result will be stored in destination register RD. Next one, and.w space rd comma rn comma ash immediate. That is, immediate data is specified in the instruction. Immediate data will be logically ANDed with rn, and the content will be stored in destination register rd. All operations are performed in bitwise. Next, and.w rd comma rn comma rm. So here you can observe that we have three different registers here. So all these three different registers can be from R0 to R12. Okay, now which are the two source registers? Rn and Rm. The content of Rn will be logically ANDed with content of Rm. Result will be stored in Rd. The difference out of these three instructions is, first instruction is used for 16-bit traditional thumb instruction set. The other two are used for used as a syntax for 32-bit thumb 2 instruction set. So the next set of instructions is logical OR operation, that is bitwise OR operation. The mnemonic used here is ORR space, there is a space here, ORR space RD comma RN. Source registers are RD and RN. The result will be stored in RD back again. So you have RD bitwise OR operator along with RN. Result will be stored in RD. Similarly, we have next two instruction. Next instruction will be given with the immediate data along with three different fields, RD space RN space immediate data. So register content RN will be bitwise OR operated with the immediate data. Result will be stored in RD. Next instruction, ORR.W space RD comma RN comma RM. Here the source registers are RN and RM. So Rn bitwise logically OR operated with Rm. The result will be stored back in Rd. Next set of instruction is bit clear, that is BIC. So BIC is nothing but you are negating, that is complementing one of the operand, that is source operand, and then you are adding it with the other register, other operand. Let us see the instruction. BIC RD comma RN. The content of RN is complemented first, then the result of the after complement will be logically ANDed with the content of RD, and the result will be stored in RD register. Next instruction, BIC.W RD comma RN comma hash immediate. So in this instruction, immediate data will be complemented, and the result of that complement will be logically ANDed with the register RN, and the result will be stored in destination register RD. Next instruction, BIC.W RD comma RN comma RM. All the three registers are different here. So the content of RM will be complemented, and the result of complement will be logically ANDed with RN content. Result will be stored in RD, that is destination register RD. Next set of instruction is for the operation bitwise or not. Okay, so the mnemonic used here is ORN, ORN dot W RD comma RN comma hash immediate. RD here the content, whatever the immediate data is given in the instruction will be complemented, and the complemented data will be uh, or operated with the content of Rn, and the result will be stored in Rd. Next instruction, ORN.W RD comma Rn comma Rm. The content of Rm will be complemented, and it will be logically or operated with the content of Rn. Result will be stored back in destination register Rd. Next set of operations are based on bitwise exclusive or operation. The mnemonic used for exclusive or operation is EOR, EOR RD comma RN. The content of RN is exclusively ORed with the content of RD. Result is stored back in RD. So all these operations are for 32-bit data, and registers used are 32-bit data. And next instruction is EOR.W RD comma RN comma hash immediate. So immediate data will be exclusively ORed with the content of RN. Result will be stored back in RD. Next instruction is EOR.W RD comma RN comma RM. The content of RM will be exclusively ORed with the content of RN. Result will be stored back in RD. I hope the logical operations are easy and you have understood. Next, we will move to the next set of instruction, that is shift and rotate instructions. In most of the question papers, they have asked the shift and rotate instructions. So let us start with the operation of rotate and shift instructions. So first instruction is for arithmetic shift right. So the mnemonic used for arithmetic shift right is ASR. Now let us understand the operation of arithmetic shift right, then we'll move on to the syntax instructions. Now the register whatever is shown here is a 32-bit register on which you are operating on, and you are performing arithmetic shift right. You are shifting the data towards right, and it is again bitwise. Suppose if you are shifting one time, then it is 1-bit shift. Suppose you are shifting 2 times, then it is 2-bit shifts. Now we have the operation for ASR. Now suppose if you are shifting for one time, let us say the least significant bit will be moved to the carry, and most significant bit will be retained in the same position as it is. Okay, that will not change. The importance of arithmetic shift right instruction is it retains the sign bit, because most significant bit will be considered as a sign bit. So it is used for retaining the signed bit in the data or the register. Now one more point you have to note here is we do not have arithmetic shift left instruction, because in arithmetic shift left operation what happens, it is just the reverse. There is no significance for the least significant bit in order to retain that. Therefore we have only arithmetic shift right, we do not have arithmetic shift left. You have to note this point. Now let us start with the first instruction. ASR RD comma RN hash immediate. The number of times you need to shift the data will be given here. So it is the content of Rn will be shifted the number of times given in the immediate data in the instruction. Result will be stored back in Rd. Next instruction is ASR space Rd comma Rn. The number of times you are going to shift the content of Rd will be present in Rn. It is shifted towards right. Then the result will be stored back in Rd. Next instruction ASR dot W Rd comma Rn comma Rm. The number of times you have to shift the contents of Rn, arithmetic shift right, the contents of Rn will be present in Rm and the result will be stored back in Rd. That means suppose if you want to shift towards right 2 times, 3 times, 4 times, 5 times, that number of times has to be present in this field, that is immediate data in the content of Rn, in the content of Rm. Next instruction is for the operation logical shift left. Let us first understand the operation of logical shift left, then we'll move the instruction. So the left shift operation, logical left shift operation is performed as shown here. The most significant bit, the register is consists of 32-bit data, that is from 0th bit to 31st bit. So here you have 31st bit as a most significant bit, right? So this most significant bit will be moved to carry. As you are shifting by 1 bit, most significant bit will be moved to carry, and at the least significant bit 0 will be included. So this is about the logical left shift. Now let us see the examples. LSL space rd comma rn comma ash immediate. So the number of times you are shifting the contents of Rn will be present in immediate data in the instruction itself. So that means uh, the content of Rn will be shifted towards left the number of times given in the immediate data in the instruction itself. After shifting, the result will be stored back in register Rd. Next instruction is LSL space Rd comma Rn. Now, the register Rd content will be logically shifted left the number of times which is present in the content of Rn. The result of the operation will be stored back in register Rd. Next instruction LSL.W Rd comma Rn comma Rm. The content of Rn will be logically left shifted by the number of times which is present in the register Rm, and the result of this operation will be stored back in Rd. So these are the 3 instructions under logical left shift. So the instructions without .w indicates that it is the syntax for traditional 16-bit thumb instruction set. The instruction with the suffix .w indicates that these are the syntax for 32-bit thumb 2 instructions. Next, we will see the same instruction operation in a pictorial format. That is LSL ash 5. That means you are shifting the data towards left 5 times. Okay. Suppose this is a register content from 0 to 31. How many times you are shifting towards left? You are shifting towards left by 5 times. So every time you shift towards left, the data will be moved to a carry bit from the most significant bit. So actually data 0th bit will be moved to the 6th bit, right? Starting from the bit position here, 5 zeros will be included, and this data will be shifted or started with the 6th bit. So this is how the data will look after left shift operation for 5 number of times. Next we have LSR, that is logical right shift. The same operation, now here we are shifting the data towards right by 5 times. So here least significant bit, for every right shift the least significant bit will be moved to a carry, and at the most significant bits zeros will be added. So how many number of times you are shifting the data towards right? 5. That means 5 times the zeros will be included towards the most significant bits, and from the least significant bits 5 bits will be lost, and the last 5th bit will be in the carry. Next instruction, here it is showing for arithmetic shift right. So I told you that arithmetic shift right, you are using it for retaining. It just retains the most significant bit as it is, and least significant bit will be moved to carry. Let us see the same thing here. Now, how many times you are considering, how many times you are shifting the data here? It is 5 times. Remember, the most significant bit here is 0. That means the register content, whatever you have here, is a positive operand because sign bit is 0 here. So how many times you are shifting? 5 times. That means 5 times the data will be shifted. 5 bits will be lost from this register content, and at the most significant bits the sign bit is 0, so 0 will be retained 5 times in the register. That is about ASR. You are shifting right towards arithmetic shifting right towards 5 times. So next we will see the same example, ASR, yeah, that is arithmetic shift right towards right side for 5 number of times. But we are considering in this example as a negative operand because the most significant bit here is 1. So ASR actually retains the sign bit, that is most significant bit. How many times you are shifting? You are shifting the data by 5 times. So 5 times the least significant 5 bits will be lost. The fifth bit will be in carry bit, and here as you are shifting towards right every bit, here the most significant bit which is having 1 will be retained as it is. So if you can count 1 2 3 4 5, so 5 times it is being retained, same data is shifted towards right. Okay, so this is the operation for LSL, LSR, ASR operation. So next we will look into LSR operation as we have discussed in the previous slide. In LSR, that is logical shift right operation, the least significant bit will be moved to carry, and at the most significant bit it will be included with 0. Now let us see the instruction. LSR space RD comma RN comma ash immediate. So the content of register RN will be logically right shifted by the number of times given in the immediate data in the instruction, and the result will be stored in RD. Then next instruction is LSR space RD comma RN. The number of times you are going to logically shift right will be present in Rn, and it will be operated with the content of Rd. Result will be stored back in Rd. Next instruction lsr.w Rd comma Rn comma Rm. The content of register Rn will be logically right shifted the number of times present in Rn. Result will be stored in Rd. The next instruction is rotate right instruction. Rotate right instruction has a mnemonic ROR space RD comma RN. Now let us first look into the operation of ROR, rotate right. It is without carry. Okay, rotate right without carry. So the operation here is every least significant bit will be moved to the most significant bit. Also it goes to the carry bit. It is rotating right without carry. Okay, LSB will go to MSB as well as it will go to carry. So next instruction ROR space RD comma RN. The RD content will be rotated by the number of times present in RN. Result will be stored back in RD. Next instruction ROR.W RD comma RN comma ash immediate. The content of register Rn will be rotated by the number of times which is given in the immediate data, and the result will be stored back in RD. Next instruction is ROR.W RD comma RN comma RM. The content of register Rn will be rotated by the number of times which is present in Rn, and the result will be stored back in RD. The next instruction is rotate right extend. It is similar to RCR instruction in the 8086, that is rotate right with carry. Okay, so the only difference between ROR and RRX is along with carry it rotates towards right. Okay, now least significant bit will go to carry, carry bit will go to the most significant bit for every RRX instruction execution. So RRX.W space RD comma RN. The content of RD will be rotated right, that is rotated right along with the carry by the number of times which is present in the register content Rn, the result will be stored back in Rd. So every least significant bit goes to C, that is carry. Carry will go to most significant bit. Next instructions are sign extension instruction. These two instructions are important and it is asked in most of the question papers. So let us see the first instruction. SXTB. B stands for byte. Okay, sign extension byte. Now you are operating on a 32-bit register RD and RN, which is the source register. RM is a source register. RD is a destination register. Sign extension byte. Okay, sign extend byte data into a word. Now let us see what is byte here. So out of 32 bits, what you will consider, which you will consider as a least significant byte? It is from 0th bit to 7th bit. Now, from 0th bit to 7th bit, you consider it as a 8 bits, that is 1 byte in the register RM. So whatever the bit you have, the bit value you have at the 7th bit position will be extended in the remaining bits of RM. So that means it will extend the sign bit which is present at the 7th bit. 7th bit means it is the most significant bit of a least significant byte, and the result will be stored in register RD. So next instruction is SXTH. SXTH. H represents half word. Half word means the least significant half word means 0 to 15 of the source register RM. So SXTH space RD comma RM. Here we consider a half word from 0 to 15 of register RM. So whatever the value you have at the bit position 15 will be extended in the remaining bits of register RM. That is from 16 to 31 bit, whatever the bit value you have at 15th bit, the same will be copied and it will be extended. The resultant will be stored back in register RD. Now, these are the two instructions for sign extensions. Sign extension byte, sign extension half word. Next, we will see the reverse operation, reverse instruction. We have three mnemonics for reverse instruction: REV, RD, RN. Now, all these three instructions we can observe or we can better understand with this pictorial representation. Before that, I'll just tell you the mnemonics here. REV, it just operates for the 32-bit data. REV16, it will operate for half word. And next you have REVSH, sign extension of a half word. Now let us start with the first instruction, REV.W. Okay, the syntax here is you have one destination register, you have one source register. So the data will be operated on a source register RN. RN is a 32-bit data. Now whatever the data you can see here is the content of RN register. So 32 bits of RN register. It will operate on a RN register. So each 32-bit data can have 4 bytes starting with 0 to 7, 8 to 15, 16 to 23, 24 to 31. So it's divided into 4 bytes, and the least significant byte will move to the position of the most significant byte here. Okay, so it goes to the 4th position. The next, first, second, third, fourth. I'll just name this as first position, second, third, and fourth. First position moves to the 4th position. Second position moves to third one, and third byte position moves to second byte position, and fourth byte position moves to the least significant byte position. So this is the operation of reverse bytes in a word. REV indicates reverse bytes in the word. Okay. Next instruction is REV16.W. 16 indicates half word. Now the complete 32-bit content of RN register, that is source register, will be divided into two half words. Okay. Look at this. It is divided into two half words and it is having totally 4 bytes, and it just reverses the bytes in a half word. So let us consider the first half word here. the first byte will be moved here and the second byte will be moved here. Similarly, the highermost half word will be reversed with each other as shown in the figure. That's the operation of reverse bytes in half word. That is the mnemonic is REV16. The next instruction is REVSH, that is reverse bytes in bottom half word and sign extend. Okay, so this is a 32-bit source register RN which is having 4 bytes. Okay, now you are operating on the bottom half word, that is nothing but the least significant half word. So let us now see which is the least significant half word. These two are least significant half word, right? So it will reverse those 2 bytes first. It will reverse those 2 bytes first. Now whatever the first byte you have here, it goes here. The second byte what you have here, it will come here. Okay, now this data which is moved here has some most significant bit. That most significant bit will be extended in the remaining upper half word of the 32-bit register. So the most significant bit after reversing, please take care that after byte reversing, the most significant bit will be extended to the remaining bits of RN register, and the result of this will be stored back in the destination register. Okay, I hope everyone have understood the day's instruction. So we started with the 32-bit instructions, multiplication instruction. Under that SMUL, that is long multiplication with accumulate, both for signed and unsigned instruction. Next we studied logical operation, AND operation, OR operation, bit clear, or not, and XOR. Next, we started with the shift and rotate instruction. In that, arithmetic shift right, logical left shift, and logical right shift, rotate right, and rotate right extend. Next important set of instruction is sign extension instruction. In that, SXTB, SXTH instruction. Next, we learned the reverse instruction. So reversing each byte in a complete word. And next is REV16, half word reversing. The next is half word, least significant half word reversing with sign extension. So these were the instructions which we learned in today's session. Okay, we'll stop the session.